Welcome everyone. We are moving on through energy and we are now at 5.2 and conservation of energy. So if you haven't started reading the book, please go ahead and begin reading chapter 7 in OpenStax and Coletta. Thank you. Okay, before we move on, here is basically going to be our equation sheet for this class, for this section of the class. I'm going to teach you about conservation of energy, which means we're not going to be dealing with non-conservative forces, which means we're not going to be dealing with work. In other words, just kinetic energy, potential energy due to gravity, and potential energy due to a spring. All the other forces, which are contact forces that are path dependent, we don't care about right now. Okay, so I just want to get you used to doing the calculations here. And used to working with energies that are conservative, brought by conservative forces, and we don't really care about the other contact forces. All right. So, what the conservation of energy is basically saying that energy cannot be created or destroyed. So, if you establish a system where an object's moving around, or is falling, or a spring is working on it and is speeding up or slowing down, you're not worried about anything outside of that, like friction or hand or any of that stuff. You just care about what is internal to that system. All right? So the conservation of energy is basically saying the initial energy you start with is equal to the final energy that you end with. Okay? And that's what conservation of energy means. You sum up if you look at the change in energy, that will be equal to 0. All right. So if we are looking at the conservation of energy, we don't care about work. So we're just looking at the initial kinetic energy, potential energy due to gravity, the kinetic potential energy due to a spring, and set that equal to the final of those energies. And there should be no difference between them. That means if you add all of that up on the initial side, that has to be equal to the final side. Okay, so again, we are in this system, we are not considering any outside contact forces beyond a spring. All right. So I was talking about what a system is and what we're going to be defining it. In this case, what I kind of do, which you could do, is define what is physically working on the system. So we're going to be doing a free body diagram again. So we're going to be drawing free body diagrams, and then we're going to look at all of those forces acting on the object and their vector directions. We're also going to note the velocity and acceleration vectors. Okay. We're going to note any contact forces that might be changing or parallel to the displacement vector or the velocity vector. Okay. So when we look at a system, what I'm talking about is we're going to draw like a little mini force diagram, and then we're going to note any of those force vectors that are working parallel to the velocity vector, and just ask ourselves, is this force vector due to a spring, or is it due to the weight of the object? And if it's in the same direction, then that means there has to be outside work being done on it. Okay. All right. So let's discuss the process. So when we first start doing our problems, what we're going to do is we're going to set the initial energy. Later on, we'll put plus or minus work and set that equal to the final energy. We're going to list out all of the initial energies right here, which this is the initial energies. This is energy initial, or it could be energy final. Okay. And the works are down here, the work functions. So all the contact forces that can't be classified as friction. Okay. we're going to write this equation out. We're also going to write all of these equations out and noting what causes it. Again, kinetic energy is motion. Potential energy due to gravity is the energy of height. Potential energy due to a spring is a compressed or stretched spring. That should be delta X. Okay. And then you have forces, you have force dot dx or delta d, because it can be in the y direction or x direction. And make sure if there is a diagonal vector that you're going to take the part of that vector that is parallel to the displacement vector. And then we have friction. Okay. What I also want to do is create a little mini force diagram, right? This will help us determine if there's any force vectors. So for example, if the object is moving to the right and we have a force vector to the right, well, that's going to be an outside force. That's going to be outside the system. So that will be taken care of by this work function. But if the object is moving to the right and the only forces acting on it are the normal force, say it's sliding on a smooth system, a smooth surface, and it's moving to the right, but it's not speeding up or slowing down, well, there is no force vector that is parallel to this velocity vector. Therefore, there are no outside works or non-conservative forces acting on it. So then we only have this. Okay. But if we had a spring pushing it to the right, well, now we've got a change in our velocity, and that would be caused by this conservative force. But if that was a force different from a spring, well, now you're dealing with an outside work or force. You'll see what I mean when we get to it. But for right now, we're not going to really worry about these outside work functions right now. We're only going to be dealing with motion, height, and springs. Okay? And we'll talk about the procedure. Okay? I don't know why that is down there twice, but that's weird. All right. So let's talk about what the evolution of this is. Okay, so let's say we had, let's talk about where conservation of energy comes from. Okay, so if we saw this earlier in the last part, you drop a ball and it starts to, in 5.0, you drop a ball and it starts to speed up as it travels downwards, right? Well, when you raise a ball up into the air and you hold it there, you hold it, and these are pie charts, you're adding potential energy to the system. So this is all potential energy due to gravity, okay? You've lifted it 1 meter up and you're holding it in place. It's not moving, and it's at a height 1 meter, okay? Later on, when the ball has almost hit the floor, it's about touching the floor and it's at its maximum velocity, but it's at its lowest height, which is basically 0. Well, this is all kinetic energy in the end, okay? Now, what conservation of energy is it says this initial energy that you added here has to be equal to this final energy. So this is the final energy. This is the initial energy, okay? So it's going to transform, this energy is going to transform from potential energy due to gravity to kinetic energy, okay? Now, halfway up, you could see if you're halfway up, it's going to be half potential energy due to gravity and half kinetic energy, okay? So if halfway up, it's got half the height, so therefore the other half of that energy has to be kinetic energy, okay? 3/4 of the way up, well, it's got 3/4 the height, so the other 1/4 had to be converted to kinetic energy, right? as it started to fall, it started to speed up. So that potential energy, that energy of the height, got turned into speed. Okay? And then it's half and half. And then finally, when we get to it here, right at 3/4 of the way up, well, now kinetic energy has consumed most of that potential energy. And now it's almost all kinetic energy. It's at 1/4 of the way up, it's going to be 1/4 potential energy due to gravity and 3/4 kinetic energy. Finally, when it hits, right before it hits the ground, it's now all kinetic energy. So this is the evolution of energy, okay, from start to finish. Now, if we do our little force diagram, we've raised the ball up to a height, and then we've let it go. The moment that we've let it go, it's going to begin moving down in the negative y direction, and it's going to begin accelerating down. But it is not going to be moving or accelerating in the x direction if you've just lifted it straight up and then let it go. And so we're going to put our non-contact force here, which is mass times gravity. And then we're going to ask ourselves, is any other thing physically touching the ball as it's falling? No. So there are no outside forces here, okay? And the only force that is parallel to the direction of motion, which the velocity vector is the direction of motion, which is also the displacement, okay? It's analogous to being the displacement. What that means is that conservative force or that potential energy is the only thing acting on it, and there's no outside forces outside of this. So this is perfect. So we've just basically looked at asked the question if there's any forces outside our system, and our force diagram helps us with that. Okay. Now, let's put some numbers into this and take a look at this. All right. So, same problem. We're going to raise a ball up 1 meter off the floor, hold it in place, and this ball is 1 kilogram, and then we're going to let it go. All right. And then we want to see how fast it's moving right before it hits the floor. Okay. Now, here's the procedure. So first, again, we're going to start off. We're going to note our velocity vectors and acceleration vectors. It's moving down in the negative y direction. So that's negative. And it's going to be accelerating down in the negative y direction. So that's negative. The only force acting on it is the weight or the earth pulling it down. Okay. And there's no outside forces. So once we've noted that, now let's write our equations out. We write this equation and we write all of these equations. And then here's what we're going to do. It's just going to be our yes or no question. So again, if we have a picture here, it's at a height. It's not moving, and its height is equal to 1 meter. And this is the initial energy. Now, right before it hits the ground, it's got its maximum velocity, but its height is equal to 0. So this is our final energy, right? Just like the pie chart showed us. So let's take a look at the initial energy. Now, these are just yes or no questions. Since we've listed out all of the kinetic energies and potential energies here, we're going to just look at the initial energy right here and ask questions. Is it moving initially, yes or no? No. Is it a height off the ground? Yes or no? Yes. Is there a spring attached to it that is compressed or stretched? No. Okay. Now let's think about the final energies. Is it moving in the end? Yes or no? Yes. Is its height, does it have a height off the ground? No. Is there a spring touching it that is compressed or stretched? No. So the initial energy is all just potential energy due to gravity, and the final energy is all just kinetic energy. Okay? Now, since we have U sub g, look over here. Everywhere I see U sub g, I'm going to replace that with mgh. The I gets tagged on to the last variable. Everywhere you see a k, you're going to put in a 1/2 mv squared. The f gets tagged on to the last variable. This should be delta x. Okay, so anyways, now we're going to actually just put in the numbers. So the initial, so the mass is 1 kilogram. Gravity is 9.8 meters per second squared, and the initial height is 1 meter. That's going to be equal to 1/2 times 1 kilogram times the final velocity squared, which is what we're trying to solve for. This is what we're trying to solve for. Okay, so I'm going to multiply this out, and I'm going to estimate this. Let's just call this 10 joules. All right. It's not exactly 10 joules. It's 9.8 joules, but let's just call it 10 joules for now, or just consider it as being analogous to 10, right? All right. So 10 joules, 1/2 times 1 kilogram is 0.5 kilograms times V final squared. We're going to divide that 0.5 onto the other side. When we do 0.8 joules divided by 0.5 kilograms, that's going to be equal to V final squared, which is going to be equal to 9.8 divided by 0.5, 19.6. So I'm going to keep that up. So V final squared is equal to 19.6 joules. Now we have to square root both sides. So I'm going to take that 19.6 and I'm going to square root it. Oops, I squared it. Square root it, I mean 4.43. So the ball will be moving at, the 1 kilogram ball will be moving at 4.43 meters per second right before hitting the ground. Okay? And that is our final velocity. Now, I put this energy versus time graph in here so we could see what is actually happening. All right, and I'm going to go ahead and put some equations over here, right? So the potential energy due to gravity, we had worked that out. That's equal to the final kinetic energy. So we had worked out that potential energy due to gravity is 9.8 joules. And since potential energy due to gravity is equal to the kinetic energy, the final kinetic energy is 9.8 joules, right? If you take 4.43 and square it and multiply it by 1 kilogram times 1/2, I'll just prove it to you. 4.43 times 4.43 times 1 kilogram times 0.5, 9.8, right? So the same thing. If you look at this, look at the change in energy from the initial energy to the final energy. So we're going to plot initial energy compared to the final energy. The initial energy is 10, and after, like, say, a period of time like 6 seconds, well, actually, let's figure out how long it took to fall to the ground. Well, let me see. Let's see how long it would take it to fall a distance 1 meter. So velocity is equal to displacement over time. And so what that means is displacement is going to be equal to change in velocity times, actually we need to find out what time is. So time is going to be equal to displacement over change in velocity, and that displacement is 1 meter. The change in velocity, it started at 0 meters per second and went to 4.43 meters per second. So that delta t is going to be equal to 1 meter over 4.43 meters per second. So I'm just figuring out for context how long it took. So 1 divided by 4.43, 0.225. So let's just say that these are not numbers, and this is just 0.225 seconds. That's how long it took for it to fall the distance 1 meter. Okay, well, if you look at it, its energy isn't changing. It started here at 10 meters per second, at 10 joules at 0 seconds, and it had it ended with 10 joules at 0.225 seconds. Okay, the slope of this line is 0, so that means power is equal to 0, which means there's no energy entering or leaving the system. So if power is 0, then that means the energy is conserved. Okay, so an energy versus time graph is another way to double check if there are any non-conservative forces affecting your motion right here. And there are not in this case, since that slope is 0. Okay? Okay, let's test our understanding of conservation of energy. Let's say you had 3 balls of the same mass starting from the top of each one of these ramps. Okay? And they're all 3 at the same height. Which ball will make it to the... so I'm going to ask you a series of questions. This first one is which ball will make it to the bottom of the ramp first. So, which ball will get to the bottom of the ramp first? Okay? So they all start from the same height. Which one will get to the bottom of the ramp first? Pause the video now. Okay. All right. Now, after asking you that question, we'll come back to it. All right. Now, same situation, but now which ball will be moving faster at the bottom of the ramp? So which ball do you think is going to be moving faster at the bottom of the ramp? Try to answer this question and pause the video now. Okay. Last question, almost done. We have 2 balls of different masses. One's got twice the mass. One's got twice the mass of another one. They're both on the same ramp. Which one do you think will be moving faster at the bottom of the ramp? The heavy one, the light one, or will they have the same speed? Try to answer this question and pause the video now. Okay, well, let's take a look at this. Again, I want you to do a mini force diagram just to see what's going on with this. So let's answer which one will be moving faster at the bottom of the ramp first. Okay, and so now they're all starting from the same height. And we'll call this 1 meter up. 1 meter up. And you know what? Let's call all of these 1 kilogram. So 1 kilogram, 1 kilogram, and 1 kilogram. They're all 1 meter up. Okay? And they're at a height 1 meter initially, and their initial velocity is equal to 0. You're just holding them in place, and then you let them go. When they get to the bottom of the ramp, their velocities are going to be greater than 0. But their heights will be equal to 0. So what I'm doing is I'm describing the initial energy and the final energy. Okay? Let's do a mini force diagram for all 3 cases of the ball as it's midway rolling down the ramp. and these are frictionless ramps. So mg is acting down on this. The normal force is going to be acting up here, away from the ramp. And remember, if from your force diagrams, the inclined plane stuff, that theta will be this theta. And so this is going to be the mg vector in the y direction, and this part is going to be the mg vector in the x direction. Okay, so this is going to be mg cosine of theta, and that'll be negative. Try to write that over here. mg cosine of theta, and that's negative. This is going to be mg sine of theta, and that's pointed in the positive x direction. Now, this is considered the x direction, so it is moving down that ramp, and it is speeding up as it's moving down that ramp. In the y direction, which is in and out of that ramp, it is not going to be moving or accelerating. Now, if you look at this, the normal force is being balanced out by mg, and neither of those forces are parallel to the motion. Again, that velocity vector in the x direction is pointed this way. Okay. So the only thing acting on it in that direction is mg sine of theta, okay, which is the force of, which is the weight of the object, okay. So that is the potential energy due to gravity, okay. Now, since we've determined there's no outside forces parallel to the direction of motion, now we could go ahead and do our force diagrams and confidently cross out work. Now, starting with the initial energy, take any one of these. Let's do the red one. Is it moving in the beginning? Yes or no? No. Is it a height off the ground in the beginning? Yes or no? Yes. Is there a spring that is compressed or stretched working on it? No. Okay, let's talk about the final energies. Is it moving right before, at the bottom of the ramp? Yes. Is its height greater than 0? No. Is there a spring touching that is compressed or stretched? No. So the initial energy is U sub gi. The final energy is kinetic energy final. So U sub gi is mgh, and the I gets tagged onto it. Everywhere you see a K, you put 1/2 mv squared, the F gets tagged onto that. So this is actually, weirdly enough, it's the same problem that we did over here, okay, as if we just dropped a ball from a height, okay. And when we go through the math of this, it's going to actually work out to be the same speed as if we just dropped it, okay. So again, this is going to be 1 kilogram times 9.8 meters per second squared times a height of 1 meter. That's going to be equal to 1/2 1 kilogram times the velocity final squared, which is what we're solving for. This is going to be 9.8 joules. This is going to be 0.5 kilograms. V final squared. 9.8 joules divided by 0.5 kilograms is V final squared. Now we're going to square root both sides. And when we do that, we're going to have V final is going to be equal to 4.43 meters per second. Again, you're going to take 9.8 divided by 0.5 and then square root it, 4.43. Okay, so since all of these objects started at the same height, and since potential energy due to gravity is independent of path, It doesn't matter if it's a steep slope or a longer slope. Okay, they will all be traveling at the same speed at the bottom of that ramp at 4.43. So the answer to who's moving faster is they have the same speed at the bottom of the ramp. Now, who gets to the bottom of the ramp first? Obviously, the one with the shortest path is going to get to the bottom of the ramp first. So A is going to take the least amount of time to get to the bottom of the ramp. So that first question, who's going to get to the bottom of the ramp first? A. Now, just because it gets to the bottom of the ramp first doesn't mean it's traveling any faster than the other balls. Okay? And in fact, we had just learned if they're on a ramp or if you're just dropping it a height 1 kilogram and it's going straight down, it's going to be traveling the same speed. So that's weird. Okay. All right. So who gets to the bottom of the ramp first? A. Who's traveling faster at the bottom of the ramp? All of them have the same speed. Now over here, we're going to do the same thing that we just did and go, but who has a greater speed if it's got one ball has twice the mass than the other one? Stands to figure, like if it's got twice the mass, it's going to take longer to speed up, and it's also going to take longer to slow down. That's what what we all think, right? Now, again, it's going to be moving down the ramp in the positive x direction, and I think I put that this should be positive x direction over here. Sorry about that. And I'm actually going to just copy. They've got the same force diagrams. Let's do the 2 mass object, right? So the 2 mass object is going to be 2 mg down. And then again, this is going to be our little areas there. And this is going to be 2 mg cosine of theta, whatever theta is here. It's in the negative direction. The normal force is pointing in the positive y direction. Negative 2 mg cosine of theta is pointing in the negative direction. The only thing causing it to speed up is 2 mg sine of theta. And that's moving in the positive x direction. That vector is pointing. So since this is the only thing pointing in the same direction as the velocity vector, and that is caused by a conservative force, we just have to deal with potential energy. Okay? Now, going over to here, so we just plotted the red ball going down the ramp here, which turns out to be all 3 of these cases. Let's do the 2 mg ball and compare these 2 things, right? This is the mg, this is the 2 mg. So again, they both start from a height of 1 meter, and they both get to the bottom where their velocity is greater than 0, but their height is equal to 0. So again, list out these equations and these 2 equations. List out all your variables here. Note the initial energy, note the final energy, and let's start doing this. So is it moving in the beginning? No. Is it a height off the ground? Yes. Is a spring touching it? No. Compressed or stretched spring. In the end, is it moving? Yes. Is it height off the ground? No. Is it a compressed or stretched spring touching it? No. So here we got UGI equals K final. So same types of energy here. Okay. And we're going to go ahead and we're going to put in MGH, but this is actually 2 MGH, which is the initial. And this is going to be 1/2 2 mv final squared. Okay. Now, if we said M is 1 kilograms, this is 2M is going to be 2 kilograms times G, which is 9.8 meters per second squared, times 1 meter. This is going to be 1/2 times 2 kilograms, which is going to be 1 kilogram, V final squared. This is going to be 9.8 times 2, what is that? 19.6, 2 times 9.8, 19.6, yep, I gotta learn to trust myself. So this side is 19.6 joules, that's equal to 1 kilogram, V final squared. Divide both sides by that mass, 19.6 joules, divided by 1 kilogram. That's equal to V final squared. We're going to square root both sides. And that is going to be V final. Okay, so 19.6 divided by 1. I know what it is, just 4.43. So okay, so whether it's got twice the mass, or so this is the 1 mass object and this is the 2 mass object, they're traveling at the same speed. Okay, let me grab something and I'm going to bring it over. I just want to point out something. So I grabbed this energy graph because I want to point something out. So I don't know how long each one of them took. Well, I'm sure if they're the same slope, since B and since this red slope, we modeled it here, and this red slope for the big object on the same slope, we modeled it there, they would take the same period of time. But I want to point out something. This guy's total energy, its initial energy and its final energy, it starts out here, and we'll call this 10 joules, and then we'll call this 20 joules, and this is positive 30 joules, and negative 10 joules, negative 20 joules, and negative 30 joules. And let's say they all took 1 second to roll down that thing, okay? Well, the smaller 1 mass object, its initial energy is 10, its final energy is 10. So this guy has, well, let's use a color other than blue, but so this guy's energy right here is a constant 10 joules from beginning to end. Now, if you look over here, and so this is for the 1 mass object, for the 1 kilogram object. The 2 kilogram object, this is its starting energy, which is basically 20 joules. So it had, for the 2 kilogram object, 20 joules starting and ending. So even though it had more energy, it was traveling the same speed. Okay? And essentially, the part that's really weird is we could have just said the masses cancel out on both equations, such that mass doesn't matter. Excuse me. When objects are in free fall, what we had learned is everything falls at the same rate. Well, this is holding true for things on a ramp too. Okay? In the absence of friction, for now, they're all moving at the same rate, although they have different energies. It's just very interesting. All right, let's try another one. And again, we're going to be doing a force diagram. So you have a ball that's lifted up a height h, and we'll call this 1 meter. and it's not moving, and it's tied to a rope, and now it's going to swing down to the bottom of its swing, where it's now at a height of 0, and its velocity is greater than 0. Okay, so I'm using the same numbers because I want to show you something that across all of these different cases. It's just so very interesting. Okay, let's do a force diagram. Now, let's do it at any point in time, like right here. You've let it go. We know the rope is pulling it up into the left. Okay, and if you look at mg, that's straight down. Okay, now it's going to be very interesting when we do this problem. Okay, because when it's at the height up here, here's the force diagram. Okay, and when it's right up there, it's actually moving this direction. Okay, and so when it's right here, and so we would have a situation kind of like when we're on the inclined plane, where this is mg sine of theta, and that is in this direction, and this is theta, which is this angle that it makes to the roof. Okay, which is the same theta over here. So these two thetas are the same. Okay, and this is mg cosine of theta. So this is at the starting position. When you look at this, what you notice is, so even at first when you look at that angle, that t is not pointed in the direction of its motion, only mg sine of theta. And then if we cut to the end of it, when it's at the bottom of its swing, try this again. When it's at the bottom of the swing, right over here, now let's do a force diagram. When it's at the bottom of the swing, that T force, that tension force, is pulling up. Our rope is pulling up. It's moving directly to the right, and it's at the bottom of the swing. Let's say right before it touches the bottom of the swing, it's still speeding up in the x direction, although it's got no velocity or acceleration in the y direction at the bottom of the swing. So again, it's moving to the right, and that tension force, even though it is an outside force and it would be considered a non-conservative, it's a non-conservative force, but since it's not parallel to the direction of motion, whether it's up here or down here or anywhere in between, it is not affecting its velocity at all. Okay, so this would be our force diagram. That T is not affecting its velocity. And so let's go ahead and start our little process. We've written out our equations. The ball's at the top here, and it's not moving. So it's not moving. It does have potential energy due to gravity, and no springs are touching it. In the end, it is moving. Its potential energy due to gravity is 0 because it's at the bottom of the swing and no springs are touching it. So what we have is a similar situation as before, as long as this is a 1 kilogram ball, right? This is height 8 meters. I want to just put it 1 meter because I want to show something going across, a consistency going across things, all of these situations. And so we have mgh, and that's equal to 1/2 mv squared. The masses actually don't matter, but I'm still going to put in 1 kilogram times 9.8 meters per second squared times the height, which is, it started out 1 meter high, and we have this for 1 kilogram, and then V final squared. This is going to be 9.8 joules, which then we're going to divide this by 0.5 kilograms. So that is going to work out to be 19.6 0.6 joules per kilogram. And we're going to square root that, and that is our final velocity. And again, what we find out is this is also 4.43 meters per second. Okay, at the bottom of the swing. Okay, so I'm doing this all to point out one thing. Whether you dropped a ball straight down, starting at a height 1 meter, or whether it rolled down 3 different ramps, but they were all at the starting position of 1 meter, not moving, or you have 2 balls of 2 different masses starting at 1 meter high, or if you lit a ball, the 1 kilogram ball 1 meter up, and it swung down by a rope, they're all traveling at the same speed at the bottom. So again, the reason potential energy due to gravity is it's independent of the path, right? So as long as they have the same starting height, they're going to be traveling at the same speed at the bottom, no matter the shape of the ramp, or no matter if it's dropping straight down or it's swinging straight down. Very interesting. Okay. Hopefully during that process, hopefully you've learned during doing those problems that the procedure for doing these problems. So let's go ahead and try something out. Okay. Let's say here you start off 8 meters high. Okay. Now you're going to shoot one ball at an angle of 30 degrees up and to the right at 10 meters per second. You're going to shoot the same ball at 10 meters per second straight out. And then you're going to shoot a ball 30 degrees below that angle, 30 degrees below, but at 10 meters per second. So they're all at 8 meters high, 10 meters per second, but being launched at different angles. Which one is going to be traveling faster right before they hit the ground? They're all taking different paths. So think about it and try to answer the question and pause the video. Which one is going to be traveling faster? Pause the video now, please. Okay. Well, let's try this out. Let's look at this. And I'm going to change this problem right here to be our situation. Okay. And a lot of people would say that this one is going to take the longest because it has a longer path, right? But it's starting out at 10 meters per second. So this is going to be 8 meters high and traveling at 10 meters per second at an angle of 30 degrees. So it gets launched at an angle of 30 degrees, 8 meters high. Let's go ahead and try this out. So once you've launched it, let's do a little force diagram. Once you've launched it, and at the moment it's leaving, the only force acting on it is mg. Okay? It's moving upwards, but it's accelerating downwards. It's moving to the right, but remember when projectile motion, it's got a constant velocity in the x direction. So this is our force diagram. You can see again, there's no outside works or forces touching it, so we don't have to worry about this. Okay, now here's where it gets a little bit different. The starting energy is here. It's got an initial kinetic energy. It's got an initial potential energy due to gravity, but no springs are touching it. In the end, it is only moving, so it doesn't have any of those two potential energies. So the initial kinetic energy plus the initial potential energy due to gravity is equal to the final kinetic energy. So 1/2 mvi squared plus mghi equals 1/2 mv final squared. Okay, So the mass, which we could cancel out right now to make the math easier, but I'm a stickler for doing things by the book. So it's 1 kilogram times, the angle doesn't matter. It just asks for what's the initial speed squared. So, which is going to be 10 meters per second squared. The initial velocity is just 10 meters per second. It's not 10 sine of 30 degrees, not 10 cosine of 30 degrees. It's just 10. And that's equal to 1 kilogram times 9.8 meters per second squared times the height, which we said is going to be 8 meters. And that's going to be equal to 1/2 times 1 kilogram times the final velocity squared. So this looks like it's going to be 100 divided by 2, which is going to be 50 joules. This is going to be 9.8 times 8 times 1, 9.8 times 8 meters times 1 kilogram, 78.84. Joules, and that's equal to 1/2 kilogram, or 0.5 kilograms. V final squared. So this side over there is going to be 50 plus 78.8. So that's 128. So it's 128 joules, 128.8 joules. And that's equal to 0.5 kilograms, V final squared. So 128.8 joules divided by 0.5 kilograms is V final squared. So if we square root both sides, we will have V final squared. So take that 128.8 divided by 0.5 and then square root it. 16.05. So 16.05 meters per second. So what you find out, since they're all launched with the same velocity, since it doesn't care the path they take, doesn't care that 30 degrees is above or below the horizontal, they will all have the same speed, and that velocity will be 16.05 meters per second. So since they all had the same starting conditions of 8 meters high and being launched at 10 meters per second, the angle doesn't matter. This is what you have. Okay? The last part of this lecture is something really interesting, because this applies to the motion of planets, right? So this is the Earth going around the sun, and we're going to do a little pie chart. If you notice, in wintertime, at least winter for the northern hemisphere, we're this far from the sun, okay? So we'll call that a distance d. Well, if you look in the summertime in the northern hemisphere, we are, if you measure that, that's about here, here, and here. It looks like our distance from the center of the sun is about 4 times that. And I'm sure this picture is inaccurate, but if you look, the potential energy due to gravity here is going to be 4 times the potential energy due to gravity here. Okay, which means this: we're going to have a huge potential energy due to gravity here. Okay, and the Earth being us related to the sun, so the gravity of the sun. Okay, and we will be moving at our slowest in the summertime. So our velocity vector is just going to be a little guy. Okay, what that means is in the summertime for the northern hemisphere, where they're further away from the sun, our velocity is going to be really small. Okay, and then as it comes around to autumn, it's going to start speeding up as we get closer to the sun, and we're speeding up in the spring. We're going to have the same speeds, but if you notice, those two speeds are greater than over here. So what that means is our kinetic energy is going to be a lot greater at that time. And so I don't know the mix of that, but let's just say it's greater by some undefined amount, which will be here. And what that means is in the spring, since it has the same velocity and it's the same distance from the sun, so those distances are the same. It'll be moving at the same speed, which will be faster. And then when we get into winter, you're going to have the opposite is going to be true. Potential energy is going to be at its minimum, and kinetic energy will be at its maximum. Again, this is during the northern hemisphere summer. Okay, which means its velocity vector is going to be 4 times greater than that. But if this was the velocity vector, I don't know. It'll actually that's not true. It'll be a lot bigger than this one. So this exchange of energy is predictive for planets going around the sun, not just people falling down. All right. And that's why it's important to study energy, because energy is predictive for very large things and also very small things. So it's a really good method of analyzing motion. All right. Incidentally, I came across this. This would be impossible, right? Because it would have, if it's traveling in a circle, okay, then that means its velocity, since it's the same distance from the sun, there's no energy exchange. And so all of these energies would be, I don't know, half kinetic and half potential, part potential, and it would be the same amount of energy, and it would be the same mix. So this is impossible. Okay, and I did come across it from a textbook, and I thought I'd point it out that you can't have a perfectly circular orbit. Okay, you have to have some kind of exchange of energies. You could have you'll have an elliptical orbit, but it just won't be perfectly a circle. It could be slightly close to a circle, but it won't be a perfect circle. Well, thank you for sticking with me. This has been 5.2 Conservation of Energy, and I hope you learned the procedure for analyzing energy. In the next module, 5.3, we'll get into what happens when you have outside forces like works or non-conservative force. Thank you. Bye.